Kepler's three laws of planetary motion. Johannes Kepler was a German in the late 1500s, early 1600s, primarily in the early 1600s, shortly after Copernicus and Tycho Brahe, who promoted the ideas of the heliocentric solar system, the sun being the center. Kepler came up with three laws of planetary motion. He also did a lot of work in optics, but he's most known for his three laws of planetary motion, as you'll see here. His first law: the planets travel in elliptical orbits, with the sun as one of the foci. Foci is plural for focus. Any ellipse has two foci. The definition of an ellipse in geometry is the set of all points at a given distance from two given points, the foci. Like a circle is the set of all points at a given distance from a given point, both of these being in a plane, not in three-dimensional space. A circle is basically a special case of an ellipse, where the two foci are the same spot. Now, we're not going to calculate the eccentricity of ellipses, but the eccentricity of an ellipse is basically how elongated it is. Now, ellipses are not ovals. They are, as the definition says, a set of all points at a given distance from two given points. In this diagram right here, the given distance would be the summation of the two red segments you see in the diagram. I'll try to highlight them. This segment here plus that segment here would be that given distance. For a circle, you have one distance. It's called the radius. But here we have the summation of those two segments being the given distance that the ellipse maps out here in this diagram. The sun is always one of the locations of one of the foci. The other focus, or foci, is empty space. I'm not going to get into all the definitions of all these things, but the main thing is an ellipse is the planets follow elliptical paths. Most of them are nearly circular. For example, the eccentricity can go from 0.0 to 1.0. The Earth's eccentricity is about 0.02. It's, from all practical purposes, circular. Pluto is quite elliptical. In fact, it's not always the farthest planet from the sun. I still consider it a planet. Neptune is sometimes further out than Pluto. That's the first law. Second law: the radius of an orbit sweeps out equal areas in equal times. Here's an example. Once again, an exaggerated ellipse. A planet going from A to B to C to D to E to F, its total orbit would be 1 year for that particular planet. So as you move from A to B, you can see these shaded regions here. I'm going to call this first region from A to B, it's kind of like a pie slice. I'll label that region A, which is the area of that pie slice. Here's region B, and say it was like for the Earth going around the sun. A to B could be 1 month, like say January. Turns out that we are closer to the sun in January than we are in August. The reason why we're colder in, well, the northern hemisphere is colder is because the northern hemisphere is tilted away from the sun in January, but that's roughly January from point A to point B there. But this is exaggerated. The Earth's orbit is nearly circular. From point C to D might be March, but that area B is the same area if you calculate it as area A. And then finally area C here, which might be September, E to F. That area, all those three areas would be equal. Another thing that this implies is that as planets move around the sun, their velocity changes, kind of like a ball falling. Now, it's not falling straight down back to the Earth, but if you go from E to F back to A, your GPE, if you're further away from the Earth or the sun, you have a greater GPE relative to the sun. Your GPE is transferring into kinetic energy. That means when you're closer to the sun, the planets are moving faster. Other good examples of this are comets. They have highly elliptical orbits. Many of them do. We will spend most of our time on Kepler's third law, which is the most mathematical of the three. The square of the orbital period, symbolized with capital T, the time for one revolution, one orbit. The time for that, the square of that time of the planet is directly proportional to the cube of the mean orbital radius. Once again, if you have an ellipse, the radius, the distance from the sun, is changing slightly or significantly over time. If we take the average or the mean orbital radius, that's part of this particular concept. I need to fill in the equations here. On your review sheet there, your note sheet, they're all filled in. Let me fill these in real fast. All these equations we've had over the past couple weeks. Centripetal acceleration in circular motion is v squared over r. Centripetal force is mv squared over r. Newton's law of universal gravity, gmm over r squared. And the relationship between weight and mass, weight equals mg. Now when you're in circular motion, the weight, W, is the force of gravity. So if we take the above equations in the blue box and plug them in here, we have mg equals g m1 m sub 2 over r squared. Now the mg on the left hand side here, that's the small mass, m sub 2. Let me put that in there, m sub 2. That would cancel out on both sides, so you get g equals, that's little g, equals capital G m sub 1 over r squared. That equation right there is useful for finding the acceleration due to gravity on the surface of any given planet with mass m and radius r. On Earth, that comes out to be 9.8 meters per second squared. But the other thing you can do with this equation is that you can also figure out the value of g at any given distance from the center of a planet. You don't have to be on the surface, but on the surface of the Earth it comes out to be 9.81, but anywhere off the surface, as r gets bigger, your distance from the center of the Earth gets bigger, the value for g will get smaller. And once again, it's an inverse square law, so if you double your distance from the center of the Earth, the value for g will go down by 1/4, or be 1/4 its original value. We also know that when you are in circular motion, the centripetal force is the force of gravity. If we write that down, F sub c equals F sub g. We look in the blue box off here to the left and plug in the appropriate equation. That is mv squared over r equals capital G m sub 1 m sub 2 over r squared. And this on the left hand side, once again, that's m sub 2. So if you cancel the m sub 2's on both sides and divide out one of the r's on both sides, excuse me, you get v squared equals g m sub 1 over r squared, no, over just r. If you take the square root of both sides, what you get is v equals the square root of g m sub 1 over r. That's useful for finding the velocity of satellites. Let me just write that down. I'll use blue. Velocity of a satellite. And for example, that you could use that to figure out the velocity of the moon. The moon is a satellite of the Earth. We have a bunch of man-made satellites, a lot of them. But one thing to note here, in that equation, the velocity of a satellite does not depend on the mass of the satellite. It depends on the mass of the Earth, which gives me a moment to pause here as well. If you look back at the diagram with the sun and the Earth over here on the left, v sub t in that diagram is the tangential velocity of the orbiting object. In this case, it's the Earth. But it also could be the moon around the Earth or any man-made satellite around the Earth. But here's one simple diagram. A couple things to keep in mind here. The sun or the central object is always mass sub 1. The orbiting satellite is always mass 2. And then we have the distance from center to center, that's our r. From center to center, which is always the assumed published number when you see them in print. Okay, moving on a little bit further here, putting some things together. I mean, we're really coming up with some new equations, but really they're combinations of the 4 equations in that big blue box on the left-hand side. But going back to some other equations we've had, and that is, for example, our simple one, v equals d over t. Well, when you're in circular motion, if you take your most convenient distance, which is one orbit, which is a circumference 2 pi r, if you take 2 pi r as our distance one time around, and then plug in capital T. Capital T here is specific for the period, the time for one revolution of some orbiting object or something that's cyclical. Well, now, if we take, and I'll circle it in black, this, all right, and plug it in for v squared. Actually, let me go to the right here and square everything over here in this equation on the right, and that is v squared. If I square the left-hand side and the right-hand side, that gives me 4 pi squared r squared over capital T squared. So over here on the right-hand side, I have v squared equals that 4 pi squared r squared over t squared, and on the left, in the black circle, I have something else that's equal to v squared from the previous calculation there. So therefore, I can plug this in for v squared. In other words, I'll go back to red. I get g m sub 1 over r equals 4 pi squared r squared over capital T squared. Now if I cross multiply that mess, I end up with g m sub 1 t squared equals 4 pi squared r cubed, because I have r times r squared is r cubed. And then I divide both sides by the gm1. I'm getting the t squared by itself. So I end up with t squared equals the 4 pi squared, which is a constant, divided by capital G m sub 1 times r cubed. I want to concentrate here on the t squared and the r cubed, because this really is Kepler's third law here, combining all these equations and manipulating them as such and solving for, well, t squared. Leaving the t squared by itself this time, what we see here is the relationship between t and r. T squared is proportional to r cubed, where the constant of proportionality here, I'll put it in parentheses, is this 4 pi squared over gm, where m sub 1 is the mass of the planet that's being orbited. The t and the r would refer to the period of the satellite in its orbit and the average radial distance of the orbiting satellite from the center object. Once again, noticing that the mass of the satellite does not matter. So that last blue box there is Kepler's third law. So let's apply Kepler's third law here. That is t squared equals 4 pi squared over capital G m sub 1 r cubed. The Earth is orbiting the Sun. It has a mean orbital radius of 1.49 times 10 to the 11th meters. And we want to calculate the mass of the Sun. Let's assume we don't know the mass of the Sun, but we do know that T equals 365 days. Let's ignore the 0.25 extra days. But 365 days. If you do the conversion there, that's like 8,760 hours. Let's multiply by 25, and then multiply that by like 3,600 seconds in every hour. That's 3.15 times 10 to the 7th seconds in a year. So we all get like 32 million seconds per year as a gift. 3.15 times 10 to the 7th seconds per year. That's the orbital period in seconds, which is a standard unit. If I plug that in over here for t, it's going to get a little messy. 3.15 times 10 to the 7th squared equals 4 pi squared over g, which is 6.67. That'll always be given to you, times 10 to the negative 11th, it's negative 11th, times mass number 1, mass sub 1, the mass of the Sun, the object being orbited, times the radius cubed, make sure it's in meters, which it is, 1.49 times 10 to the 11th cubed. Now what makes this fun for me and for some of you is that how often do you get to do a cube? And your calculators are powerful enough to do that. There's a cube function somewhere on the calculator. What I usually just do is use the caret button to the third power to cube that. I could have solved this for M1 before I plugged the numbers in, but I'm just going to go to my calculator, plug all those numbers in, and move things around. In other words, I would move the M1 to the left side and move the 3.15 times 10 to the 7th squared to the right side. You'll be dividing by that. when all is said and done, and you might want to pause this once again and see if you can do that, because there's a lot of number punching here on your calculator. It's easy to make a mistake, but you should end up with mass number 1, mass sub 1, the mass of the Sun, as 1.97 times 10 to the 30th kilograms. The more common published number is 1.99. Don't let that alarm you. But that's what it comes out to be if you plug in the appropriate numbers for the period of the Earth's orbit. I guess if you plugged in the extra quarter day, that would make the mass even smaller, but not by much. Probably not significantly any different than this. But Kepler's third law.